alkanes. Halogenation or photochemical reaction. In this module, let us study about the halogenation reaction. The addition of a halogen atom in a molecule is called halogenation reaction. Halogen, in the presence of sunlight, dissociates into radical and substitute hydrogen from alkane, resulting in alkyl halide. Methane, on reaction with chlorine gas in the presence of sunlight, produces chloromethane, thereby eliminating one molecule of hydrogen chloride. It is important to understand that the reaction will proceed until all the hydrogen atoms are replaced by halogen. It is important to note that halogenation is supposed to proceed via free radical chain mechanism involving 3 steps, namely chain initiation, chain propagation, and chain termination. Chain initiation. In this step, reaction is initiated by a radical homolysis of chlorine molecule in the presence of light or heat. Which results in the formation of chlorine-free radicals. The reaction is shown here. The next step, chain propagation. In this step, the substrate produces product and that product produces substrate again. This step repeats itself until one of the substrate is consumed completely in the reaction. The reaction keeps on going due to the chain reaction. Let us understand this in detail. Chlorine-free radical attacks the methane molecule and takes the reaction in the forward direction by breaking the CH bond to generate methyl-free radical with the formation of HCl. The reaction is as shown. The methyl radical, thus obtained, attacks the second molecule of chlorine to form CH3Cl with the liberation of another chlorine-free radical by homolysis of chlorine molecule. Thus, chlorine produces methyl-free radicals and vice versa, and thus propagates the chain. The final step is the chain termination step. In this step, we terminate the reaction. Chlorine-free radicals are provided from outside, which consume the already present chlorine radical and thus stop the reaction. The reaction is as shown here. Part 1. In this module, let us understand about some chemical properties of carbon compounds. Combustion. Carbon, in all its allotropic forms, burns in oxygen to give carbon dioxide, along with the release of heat and light. Most carbon compounds also release a large amount of heat and light on burning. The reaction being C plus O2 gives CO2 plus heat and light. Also, CH3CH2OH plus O2 gives CO2 plus H2O plus heat and light. Saturated hydrocarbons will generally give a clean flame, while unsaturated carbon compounds will give a yellow flame with lots of black smoke. However, limiting the supply of air results in incomplete combustion of even saturated hydrocarbons, giving a sooty flame. The gas or kerosene stove used at home has inlets for air, so that a sufficiently oxygen-rich mixture is burnt to give a clean blue flame. If you observe the bottoms of cooking vessels getting blackened, it means that the air holes are blocked and fuel is getting wasted. Fuels such as coal and petroleum have some amount of nitrogen and sulfur in them. Their combustion results in the formation of oxides of sulfur and nitrogen, which are major pollutants in the environment. Let us now focus on another chemical property of carbon: oxidation. You have learnt about oxidation reactions in the earlier modules. Carbon compounds can be easily oxidized on combustion. In addition to this complete oxidation, we have reactions in which alcohols are converted to carboxylic acids. The reaction being CH3 single bond CH2OH reacting in the presence of alkaline KMNO4 plus heat or acidified K2Cr2O7 plus heat gives CH3COOH. We see that some substances are capable of adding oxygen to others. These substances are known as oxidizing agents. Alkaline potassium permanganate or acidified potassium dichromate are oxidizing alcohols to acid, that is, adding oxygen to the starting material. Hence, they are known as oxidizing agents. Part 2. Unsaturated hydrocarbons add hydrogen in the presence of catalysts, such as palladium or nickel, to give saturated hydrocarbons. The reaction being C double bond C on reacting with H single bond H in presence of catalyst gives C single bond C. Catalysts are substances that cause a reaction to occur or proceed at a different rate without the reaction itself being affected. This reaction is commonly used in the hydrogenation of vegetable oils using a nickel catalyst. Vegetable oils generally have long unsaturated carbon chains, while animal fats have saturated carbon chains. You must have seen some advertisements stating that some vegetable oils are healthy. Animal fats generally contain saturated fatty acids, which are said to be harmful for health. Oils containing unsaturated fatty acids should be chosen for cooking. Substitution reaction. Saturated hydrocarbons are fairly unreactive and are inert in the presence of most reagents. However, in the presence of sunlight, chlorine reacts with saturated hydrocarbons at room temperature. The reaction being saturated hydrocarbon plus chlorine in the presence of sunlight gives alkyl chloride. Chlorine can replace the hydrogen atoms one by one. CH4 plus Cl2 gives CH3Cl plus HCl. CH3Cl plus Cl2 gives CH2Cl2 plus HCl. CH2Cl2 plus Cl2 gives CHCl3 plus HCl. CHCl3 plus Cl2 gives CCl4 plus HCl. It is called a substitution reaction because one type of atom or a group of atoms takes the place of another. A number of products are usually formed with the higher homologues of alkanes. Ethanoic acid is commonly called acetic acid and belongs to a group of acids called carboxylic acids. 5 to 8% solution of acetic acid in water is called vinegar and is used widely as a preservative in pickles. The melting point of pure ethanoic acids is 290 K and hence it often freezes during winter in cold climates. This gave rise to its name, glacial acetic acid. The group of organic compounds called carboxylic acids are obviously characterized by a special acidity. However, unlike mineral acids like HCl, which are completely ionized, carboxylic acids are weak acids. Reactions of ethanoic acid. Esterification reaction. Esters are most commonly formed by reaction of an acid and an alcohol. Ethanoic acid reacts with absolute ethanol in the presence of an acidic catalyst to give an ester. CH3COOH plus CH3CH2OH gives CH3COO C2H5 plus water. Esters are sweet-smelling substances. These are used in making perfumes and as flavoring agents. Esters react in the presence of an acid or a base to give back the alcohol and carboxylic acid. This reaction is known as saponification because it is used in the preparation of soap. The reaction being CH3COO C2H5 in the presence of NaOH gives C2H5OH plus CH3COOH. Reaction with a base. Like mineral acids, ethanoic acids react with a base such as sodium hydroxide to give a salt. Sodium ethanoate, or commonly called sodium acetate, and water. The reaction being NaOH plus CH3COOH gives CH3COONA plus H2O. Reaction with carbonates and hydrogen carbonates. Ethanoic acid reacts with carbonates and hydrogen carbonates to give rise to a salt, carbon dioxide, and water. The salt produced is commonly called sodium acetate. The reaction being 2CH3COOH plus Na2CO3 gives 2CH3COONA plus H2O plus CO2. CH3COOH plus NaHCO3 gives CH3COONA plus H2O plus CO2. Let us perform an activity. Take about 10 ml of water each in 2 test tubes. Add a drop of oil, cooking oil, to both the test tubes and label them as A and B. To test tube B, add a few drops of soap solution. Now, shake both the test tubes vigorously for the same period of time. Can you see the oil and water layers separately in both the test tubes immediately after you stop shaking them? Leave the test tubes undisturbed for some time and observe. Does the layer of oil separate out? In which test tube does this happen first? This activity demonstrates the effect of soap in cleaning. Most dirt is oily in nature, and as you know, oil does not dissolve in water. The molecules of soap are sodium or potassium salts of long-chain carboxylic acids. The ionic end of soap dissolves in water, while the carbon chain dissolves in oil. The soap molecules thus form structures called micelles, where one end of the molecule is towards the oil droplet, while the ionic end faces outside. This forms an emulsion in water. The soap micelle thus helps in dissolving the dirt in water, and we can wash our clothes clean.